from University of Washington. Actually, he has become a pretty well-known figure at our school because we send a group of students to the University of Washington campus for the last year and a half, I guess, right? And our students are getting lectures from Dr. West, and he's been quite popular, right? So I'll stop at that. Let's give him a
I don't know, popularity could be infamous too. So. Okay, I'll have less time. So I will just go over some big points that we're trying to explore in my lab. First of all, let's see here. Let's see one of the slides. Oops, just a second here.
Dr. West?
Yes?
They have to excuse because they have classes with Dr. West.
No problem. Okay, if you need to go, that's totally okay. I'm going to go through some sort of big points and tell you a little bit about, well, I'll let everyone that needs to go first. You guys can go.
They're taking exam.
Oh, it's exam. Yeah.
Good luck.
Yeah, good luck. Okay, so everyone else is staying. All right. Okay, well, thanks for staying. I'll just so you know, I'll plan to talk probably around, I'll try to shorten it because I know that this was to 2 o'clock, so I'll try to finish in about 15 minutes. Okay, so what I'm going to talk about today are sort of questions and tasks that all deal with figuring out how to map large networks. That's kind of hard to see. For some reason, the contrast isn't coming out. I spend a lot of time thinking about large systems and how to find the relevant features in these large systems. This was inspired a lot by work that I did during my PhD and during the postdoc, and I continue to do in my lab now. So I did mention this to those that were in my class, but I run a lab called the Data Lab at my university, at the University of Washington, and we work on all sorts of data. This involves 4 different faculty. Josh Blumenstock, Emma Spiro, myself, and Jessica Holman. And we spend a lot of time in the areas of business analytics, ways to analyze data to help make decisions. Social behavior is a big thing that we work on. We care a lot about how to use data to help, for example, developing countries. So this picture that you see up here is a picture of a large cell phone communication system in countries like Pakistan, Rwanda, Afghanistan, a lot of the developing countries. And we can use this anonymized cell phone data to figure out or to sort of infer economic indicators that we couldn't before. And you can look at major events like a major catastrophe, you know, as unfortunate as it is, like an earthquake in Haiti, and you can look at how that communication system changes. And you can look at that at a large system level. We also care a lot about how these sorts of data and technologies can be used to help poverty and social change. And then we do a lot of core method stuff, network analysis. And we use as our data sets usually social media, large corpora, as David had mentioned in his set. But let me just give you an example of the types of questions or sort of the philosophy that drives a lot of our methods first. So this is a picture outside of the university where I did my postdoc with Martin Rosball, and this is a picture that he put up. This is his picture, and I think it's one of the best examples of the sort of underlying principles to the methods that we use in our lab and also in many other labs that work on this kind of problem. What you're seeing are 2 images. Those 2 images are the exact same size. By the way, this is an ice sculpture in northern Sweden. This is a picture that if you measured the size on a computer, it's 5.8 megabytes. And if you measured this size, it's also 5.8 megabytes. They're both uncompressed images. If you were to use a standard compression on your computer, any sort of standard compression, and you were to compress this image and then compress this image, you'd find that you could only compress this one to 2.8 megabytes, and you could only compress that one to 0.98 megabytes. And why is that?
more patterns are in the below picture.
You're absolutely right. There's more patterns here, so when you compress that information, you can only compress it so much. And that's the philosophy that drives a lot of the algorithms we do. So those of you that are involved in statistics, there's a really interesting area of statistics called minimal description length. It's an area that describes data on how well it can compress that information. There's the duality, this duality between compressing information and finding patterns allows us to do all sorts of interesting things. And one of the great examples of this is this thing called the map equation, which was developed out of my lab when I was a PhD student. And this sort of, we call it the map equation. This equation describes very complex systems and or minimizes the description of these complex systems. Any kind of complex system that has some sort of network property, like disease networks, like traffic transportation networks, like banking networks, like citation networks in the literature. You don't need to know the mathematics, but all you need to know is that it's doing the same thing. It's taking in a bunch of data and compressing. So let me give you my favorite example of applying the map equation to a data set. In this case, many of you already know that the citation literature, the literature that you read, books that you read, things on the web, ideas are linked through citations, hyperlinks, or footnotes, or common language, or co-authors. And it builds this vast, humongous, enormous network that contains billions of nodes and hundreds of billions of links if you had the whole thing. Now, no one has the whole thing. Maybe some of the search engines have as close to the whole thing as possible. But there's a real challenge when you start to scale these things up. And this is a small data set, but we took 10,000 journals and 60 million citations, and we wanted to see if we could visualize this. Turns out it's really, really hard to do that on that kind of network. Imagine how it would be on some of these bigger networks. But our goal is to see what happens when you try to compress this data set. And I'll tell you why we want to compress this data set, because if you don't compress it, this is what you see, a big, big mess. Now this is only a portion of that network. It's only a very, very, very small portion of that network, where the nodes here represent journals and the links represent citations. But I can tell you, because my lab works on even much bigger networks than this, it's a bigger mess than this. So this is one of our big challenges. We want to figure out how we can compress this data in a way that reveals structure and reveals the important elements in a large, large data set. So we want to go from that to this. Something that gives us some idea of the structure of what that system looks like. So in this case, what you are looking at is a map of science. It was one of the first ones there's been lots of maps of science, but the first ones that applied this method to the data. And you can immediately start to see major structures of science. So using these 60 million citations, we can see that there's a major set of ideas being exchanged between chemistry and physics. And we see this backbone of physics and chemistry into the molecular and cellular biology areas and neuroscience and medicine. And you can see computer science up here and probability and statistics and economics. And these things, the reason why this is a nice way to start, this is a nice data set to start doing this on, it's because we actually have an idea of what things are connected. If there was no connection between, let's say, physics and chemistry, a strong connection, something's wrong with the method. So it's a lesson in our lab. We're always looking for data sets that, one, are interesting, and the scholarly literature to me is one of the most interesting data sets we work on, because we can look at the formation of ideas over very long periods of time. And this particular data set, after doing it, we can see that the structures do make sense. So then we can apply this to lots of other data sets. So we can take any kind of data set or any network that has nodes that represent, let's say, people, or books, or paper, or bank, or car, or government, or country, and links are how they interact. I generally work on the scholarly literature, and this is borrowed from Martin Roswell. He's a network scientist, and this represents all of the scientists in the world that are working in this particular area. And it's only 1,000, and you can see how messy it is. But again, if you use these same sort of methods, you can start to pick out the structure. Then you can start to learn what this system looks like by asking this algorithm to find the relevant features, the important features. Because unfortunately, most of big data is represented like this, a big mess of data. And I work in the information science areas. I'm in an information school. And we deal with this problem all the time. We deal with trying to come up with ways of organizing information and building automatic ontologies and classification schemes. So we're using this kind of information and this technology that we've developed and we continue to develop so that we can apply this to a lot of the problems we have in information science. You can do things more than just organize. You can then start to build recommendation systems around this. You can start to understand sort of the ontology of ideas and why some things have come together. You can study things like innovation. You can study better ways of improving information retrieval. You can start to understand things about knowledge organization. These are the sorts of questions that information scientists in my field are really excited about. Now, many of you use search engines every day. I certainly do. I learned something interesting in Korea while I was here. I found that Google is not the primary search engine. It's one of the first places on this earth, and I'm so happy to hear that. I hope that Naver stays around. Am I saying it right, Naver?
Yeah.
I hope it stays around because I want Google to have some competition. I personally use Google too much. But underneath the technology that Google has that allows us to find things, it takes advantage of structure like this. They have different algorithms, and we have algorithms that are similar, and we've talked to, I was just at Google in Mountain View before I got here at a conference, and we're exchanging ideas on how to do this. But Google is basically a company that comes out of information science schools and computer science schools. That is the ultimate organization project, and that's what we do. So we want to go from here, we want to move, we want to also not just get structure, we want to then start to want to build hierarchical structure. And once you have this hierarchical structure, then you're really in a good position. So one of the big projects that I have at my lab that I started several years ago is something called eigenfactor.org, and it provides these maps for free and tools that you can play around with and visualizations. Because a lot of this is in method building, but just as much, it's also about tools, information visualizations tools. So a part of my lab also works in the area of human-computer interaction, which is all about taking complicated data, applying algorithms, and then developing tools, information and visualization tools, so that people can extract that information. And a lot of it also deals with metrics. So I develop metrics for scholarly publishing, but I also work with economists on these kinds of problems outside just economic publishing. But my sort of area of expertise is within scholarly communication, economics of publishing, and also in just understanding the history of science. So we have tools that we're adding all the time, and they're all free that you can use and play around with. So these are the kinds of questions that I ask often with that particular project. You know, I work with librarians, helping them, given shrinking budgets, how do they deal with which journals and which books they want to keep? How do you promote content if you're publishers? How do you survive in this new digital world? I work a lot with foundations to figure out, using this technology, once we have these maps and these structures, how can we help them evaluate their impact? How do we increase their impact? I help aggregators of information. I work with companies like Thomson Reuters and big information companies that deal with this all the time. And then I work with governments and people that are working in big data. So most people would market me, market my lab as sort of a big data lab, but we're very interested, my big personal interest is in scholarly communication, and using that as an example for building good tools that can be applied to other things. And I'll give you examples in the way this technology is being used outside of information science and outside of the library sciences, which is where I normally spend my time. But it's all about dynamics. Right now, it's one thing to get a static image, but what we're trying to capture are the dynamics of these things. So what is dynamics? Dynamics is really just, what it means is trying to capture sort of movement and flow in these very complicated systems. So in the science system that I gave you, the literature, ideas are flowing all the time. So we want to figure out how to capture it and take snapshots and movies of it. And we want to figure out how do we capture the movement of individuals at the individual scale when you're flying from one place to the next, and then look at it at the system level. Look at how the dynamics of the system level can tell you something about the individual level and vice versa. Or in a banking system, a financial system, the individual dollars, the transactions that are happening between consumers and the commercial vendors or the banks themselves. So here's the banks. How do we then, track the movement of monetary flow at a very, very large scale? And I have colleagues that have been working on this quite significantly for several years, using, again, the same tools that I've mentioned at the very beginning, based on trying to develop methods that compress information. And my favorite area is one where we look at how ideas are spreading through scholarship over time, across disciplines, and between authors. And this is based because this is all based on systems that have similar properties. These similar properties are properties where the systems are differentiated. That just means the nodes are all different, they're individuals. They're multi-partite, they have modules. They're integrated. The effect of one node can have another effect down the line. And they're incredibly dynamic, and they move from one time period to the next. So what do we use to sort of capture these kinds of processes in our world, our social world? And for me and for a long time, it's been networks. And we have algorithms we've developed, and I'm not going to talk about it here. I just want you to know that there's algorithms. But when I talk about mapping of these things, and I've talked about this so far in this talk, I'm really talking about sort of ranking the nodes, but also adding context. So let me leave you, I'll give you a couple more examples, and then I'm going to give you a couple specific examples in my lab that we're recently working on using this technology. But one of the more interesting questions for me, from a scholar's standpoint, is how do we map the evolution of ideas in science and scholarship over time? We have this great data set. We have one of the largest, probably one of the better curated data sets for research. I've spent years of my career putting together this data set that allows me to study these ideas over time. We have a data set by working with JSTOR, this is this digital archive. We have a data set of papers that go back to the Renaissance, back 600 years. Some of the first publications or journals that were ever published, we have extracted information so we can build networks over time. Now this is a snapshot of just two recent years, 1995 and 2004. And we thought, oh wow, we can actually make two beautiful maps, and that'll help us, we'll be able to tell what's going on over time. Well, unfortunately, you can't really, it's really difficult to tell the difference between the map on the left and the map on the right. And it's not showing up real great for you. I think the contrast again is a little bit off. But that challenge was starting to overcome by a method that Martin Roswell and Carl Bergstrom came up with, which is called an alluvial diagram. And we use these things all the time in our lab. So yeah, people have asked me to talk a little bit about what I've done in my postdoc, and that's what I'm talking about right now, several things, and then I'm going to give some examples of what we've done afterwards. So what you're seeing here is an alluvial diagram. And that's the same map that you saw before, but now I have a time period in 2001. This is molecular biology, this is medicine. So instead of circles, there's squares now. And so as we move in time, you can start to see a movement. There's some movement. That movement are sort of groups of journals that are moving over time. And if you highlight the major changes, you see that they're probably the largest movement structurally in science for the last 20 years has been the standalone field, the emergence of the standalone field of neuroscience. And so this has been a lot of fun applying this technique to other data. This is that federal markets data I was mentioning that was written by someone that was Rod Garrett at the Federal Reserve Banks, Martin and several other economists. Basically, they were using the same technology, and they were looking at, instead of the flow of ideas, they were looking at the flow of money over time in these different banks. So here the groups are banks and the flow of money between these banks. And you can see major changes back in 2008 around this date. So there was all this activity, and then boom, there was a bunch of banks that started sharing with each other, and here there was a split. Basically, there was a big change going on. So what was that change? Well, it was historically the first time that the Federal Reserve in the United States had ever paid interest on reserves. So this was an example of how these alluvial diagrams could be used to start to see and try to diagnose big systemic risks. So I'm going to end, because I said I'm going to try to do it in 15 minutes, and I'm at about that right now. So I'm going to end with a couple other things that I'm interested in right now, and that's trying to figure out the life history of innovation, of ideas in the patent space and in scholarship. So one of the things that I'm interested in is, when something pops in someone's head, or in a group of people's heads, how long does it take to help our general economy? Turns out it's a long time. So this is an example. He's a professor at my university. He came up with an idea in the 1970s, early 1980s. He published this paper in Nature and the Proceedings of the National Academy of Science and Cell. So he published many versions of this. These are top papers in the world, or journals. If you publish here, these are sort of the key places. So it had been vetted by the community. Then the university decided to license this to the Washington Research Foundation. It's a foundation sort of outside our university that licenses technology. That took about 7 to 10 years. And then they had to go, this patent application had to go through a lot of lawyers' hands. And there was all this paperwork that was done, and finally there was a patent that was granted by the examiners. The patent was then granted, and then it was licensed to managers at major biotech companies like Genentech and Amgen. And from that, there's actually been far more than that. Our university has generated $300 million through this one investment, or this one idea. But this one idea was spectacular. But it's also an idea that took a long, long time. It took 10, 20, 30, or it took over 30 years to get this generation. By the way, the Washington Research Foundation just this year donated, or actually just last year donated a big portion of that funds. So I guess my point is, of course ideas take a long time to generate, but now we have the data and we have some of the technology that we can start to track this and understand how can we make ideas get into sort of production even faster. So we've been dealing a lot with the patent network and extracting data from this network that now, this data set that's available. We've developed some tools that we make freely available that others can start to use. We've started to ask questions about the role of patents for scientific innovation. I have this fear that they're actually, reducing innovation, and so it's something that I'm trying to figure out what the role is. The role of gatekeepers, these are examiners, and what role they're playing in innovation. And also I'm finding all sorts of what I call shenanigans. You probably don't know this word, but the word basically means people are cheating the system. So what I wanted to know is, if you were citing, if you were an inventor and you're citing correctly over time, when you hit the expiration date, when the patent is then free to the public and it's open, the citing behavior should be the same. But if people aren't citing you properly, or they're kind of gaming the system, you'll see an uptick. So that was the hypothesis, that we're going to start to see an uptick if we saw some of these shenanigans. And as you would expect, we did see some. So what you're seeing is this patent over the 20 years of its life. The patent lasts about 20 years. And then this is the day it expired. So if everything's going normal and there's no gaming, the line should be pretty straight, right? What do you think happened? Aha, so there's some gaming going on. So looking at this example, this is one of many thousands of examples of gaming that goes on in PatentSphere. This company wasn't citing at all. This company called Halliburton was citing the Shell company. So this was a gas company, and they had some, so Exxon. So Exxon's one of its big competitors is Halliburton, and all of a sudden there was a lot of Halliburton. Now this isn't conclusive evidence that Halliburton's gaming or doing anything unlawful, because they're not doing anything unlawful, but what this shows you is that this system, this big large network, where we say, this is all sort of driven by curiosity, we know that there's a lot of social processes and economic processes that are driving these. So we're working with policymakers to try to use this technology to help them build better systems that can spur innovation. And I'm not going to go into this because I don't have time, but the other big project recently, and we have many projects in our lab, like lots of labs. I'm just sort of sampling some of the things that I find interesting right now. I have some students that are working on some machine learning techniques for trying to teach the computer to learn the literature, to read the literature. And this is a hard task because Google spent billions of dollars, well, I think almost billions, but billions and billions of CPU hours to try to recognize a cat. And they finally recognized the cat. So and we're not that farther ahead than that. So you can expect there's a lot of room that needs to be, a lot of innovation that still needs to happen for us to do too much more. I don't think we're going to read the literature until we can tell our computers how to recognize a cat. But what's amazing is actually in the last 2 years, so this happened not too long ago, but in the last 2 years, it has exploded, this area of deep learning, and computers are doing a lot more than just recognizing a cat. So we want computers to be able to read figures and diagrams, and so we have this project called Visiometrics, and what it does is it basically can recognize and read figures like it can read the literature. And we are looking at ways in which we classify these things into different types. We have this open, we're writing a paper right now on how to extract the data from figures and from drawings, and so hopefully that'll help. Of course, again, one of the big things we want to do is facilitate innovation, measure innovation, and have the computers teach us what are the sort of characteristics of genius, of creativity over the last 300, 400, 500 years. And I like this graphic because someone went along and read all the diaries of these very important, very creative people. Chopin, Immanuel Kant, Sigmund Freud, Charles Darwin, all these very famous, Benjamin Franklin. These are all people that have made a big impact. They're very important historical figures. So the question was that this person looked into is they wanted to see what kind of routines on a daily basis made them so creative. And so this is just sort of what I'd like to do at a very, very large scale, but they did it at an individual scale. So I thought it was kind of cool. But that's kind of what we're trying to do a little bit with these machines, is try to figure out ways of facilitating innovation. So lots of people work on these projects, and I always try to make sure I give credit to those that have contributed to the work I've mentioned today, but there's a lot more than just this. This is just some. All right, so with that, I went about too long again, but that's sort of the core of what we do. We try to map large networks and use those large networks to do sort of hopefully relevant, high-impact social impact work. So with that, I'll be done.
Very interesting. Very interesting. Actually, I'm glad to see those two guys, Todd and Ted.
Yeah.
Who's big on open access.
Yeah, exactly. They're definitely on there. They're one of my two.
They found the right guy to work with.
Yeah, no, they're fantastic actually. Ted and Carl are two among two of my favorite people to work with, and then Martin too on there. And then the students I'm working with now are just also really fantastic.
So,
everyone is probably so tired. That's a lot of talking. So feel free to come up to me and talk to me afterwards, or feel free to go take a rest too. No need to.
any questions you want to ask? Okay, it's been a really information-packed session.
Exactly, it has. There's been a lot in that. That's more than a lecture. So I feel for you guys. That's more than I can pay attention to.
Well, I hope that these two talks really inspired you into learning more, challenging more. Right? Okay. Again, thank you very much for
thank you.
interesting talk. And many of us will be seeing him in a few days. Right?
Yeah,
seeing
exactly.
him next week.
Yes.
Yeah,
Next Tuesday.
Yep, next Wednesday. How many? Raise your hand. I'm just curious.
Yeah.
Oh wow, this is a big group. So actually, Sam was going to have me talk about some of this stuff. So maybe I'll change a little bit. I'll talk about them either in more detail, or what I'll do is I will talk about a specific project and dig into it.
Okay.
So yes, I'll see you all. Enjoy Seattle. It's a lot of fun. I think you've got a lot of things planned.
Yeah.
You're going to see a lot of different places, and if you have questions, let me know. But yeah, I'll see you on the other side of the ocean. So.
Okay. Yeah.
Before you go, and we have a final cut for photos, group photos.
Yes, group photos.
Group photos. And remember, if I have your tickets in my office, please stop by. You have to bring your tickets, flight tickets. Can you help us to move those chairs? signature needed this time.
Okay.
From special funding. I heard you have a team.
Yeah. Because I have to leave tomorrow, so it'll pack it.
Are you moving tomorrow?
Yes. I know. I have 1-year-old and a 2-year-old. I'm gonna go home. Yeah, I wanna go home.
You miss them a lot.
Yeah,
You
exactly.
have been separated
Yeah,
for a
3
month.
weeks, yeah.
3 weeks.
Yeah.
Right. So either